Hello again, welcome to the next video of advanced meshing of rotating geometric parts. First thing I want to do is to copy the corresponding files to the blower folder. For this I go to the USB and RAID folder, find the project, CFD projects, blower 2, and copy these files here. Then I open the preform template file or folder and go to the terminal in order to do the conversion of the Windows files to Linux format. The download is complete, the copy files are copied, so I close the USB folder, open the file for changes in from DOS to Unix. So after conversion is done, I create copies without txt intention and put them to run blower to system folder. So copy and do the following. I delete, surfaceFeatureExtractDict is the last file. Now I copy the prepared folders or files and put them or place them to run blower system folder. So I replace everything. So snappy and often foam run will be relocated. Export of Salom, I put the constant tri-surface folder. For that I go to Salom, export, copy, run folder, constant tri-surface, and put the new files inside. Then I switch now to run folder and activate the OpenFoam in terminal by typing of the following command. So I go to run folder and activate the OpenFoam. Now it's important to go through the files which are responsible for meshing. These are blockmesh, decomposeParDict, surfaceFeatureExtractDict, and of course the snappyHexMeshDict. I open them. Blockmesh is structured as follows. It has min and max points for each direction, X, Y, and Z direction. For all these points are organized to hexaeder. This is here. Each side length of the block mesh is divided by the corresponding number of cells, resulting in a cell size of 128 millimeters. For example, the X direction -5 and +17 divided to 182 gives the result of 128 millimeter. decomposeParDict has 16 cores, and the method is simple. It can also be changed to hierarchical or Scotch and so on. surfaceFeatureExtractDict contains everything that is necessary for edge mesh creation. It extracts edge features and saves them to the file eMesh located in the constant trisurface subdirectory. Here is the place where the point eMesh files will be created. Parameter includeAngle specifies an angle in degrees. 0 means that no edges will be selected, and 180 select all edges from STL file, including all mesh triangles. Remember, the edge mesh refinement will be done along these edges. So for everyone it is important to separate the different faces from each other by these edges in order to reproduce the real geometry faces. But be careful by choosing of the value 180 degrees. In this case, all edges from STL mesh file will be defined as body edges. I repeat, it will be all triangles of STL mesh, not only the real edges. Parameter write obj set to yes means the output will also be written in the obj format to the constant extended feature edge mesh subdirectory. This format can be viewed directly in ParaView. We can play around these settings in order to become the feeling what is it about. Let me open the ParaView for this. First, I set write objects to yes and start the surface feature extraction. In order to start surface feature extraction, I have to write the following command: surfaceFeatureExtract. So to visualize this, I will go to the constant extended feature edge mesh subdirectory. Here you see the walls blower point eMesh is created, and also other eMesh files are here placed. lower edge mesh, pulse rotation, for example. So now I have to change the color to visible. So you see the result. Then I change the include angle to 10 and run the surface feature extract again. Save and run the surface feature extract again. Now I update these parts by typing of F5 button. So you see none of these edges are selected. So we have for each body only one face. Now I switch include angle to 180 and repeat the surface extraction again. So now I have to update these parts. Now you see all the edges of a stale mesh file. And this is not good, because in this case we became too much cells along all of these edges. So I turn the settings to original, to my preferred settings, and go further to the snappyHexMeshDict. So it's done. I close surface feature extract and open the snappyHexMeshDict. This is how the snappyHexMeshDict looks like. I go through it and I begin with the geometry part. We have defined here 4 STL files which are located in constant trisurface directory, as you know. So then we have some refinement definitions, exactly 2 refinement boxes and 2 refinement cylinders. And now I go forward to castellated mesh controls, and it begins with refinement regions in my script as well, because I can easily compare the refinement regions with its refinement levels. So I have some definitions, min-max coordinates, and I know is it a big box or the smaller one, and here I can easily set the refinement level. If I need to change the refinement level, I can choose the right refinement zone above and set here the new refinement level. It's very practical and good. Now we have to come to an important part, and the definition of refinement surfaces is mentioned, and in this definition is important to mention the rotating zone, because this definition controls the rotation. The setup is different in comparison to other refinement surfaces. You can see the differences here, and for example, and for other walls, the definition starts with levels as usual, levels, but then we have the settings for face type, cell zone, face zone, and cell zone inside. These definitions I took from the tutorial rotating fan in room. Now I will show you the definitions in this tutorial. This is the tutorial, and here is the definition of rotating zone. First, we have the same structure. We have levels, and then you see that all definitions match to definitions in my script. So cell zone inside, cell zone rotating zone, and so on. Now we come to another important point. This is the point of allow freestanding zone faces, and it is set to true for meshes with zones. It should be selected as true, and of course we have rotating zone. So the allow freestanding zone faces is there. That's why true. Here I wanted to take closer look on snapControl tolerance option. This is here. Tolerance means the maximum relative distance for points to be attracted by surface. In order to show you the meaning of it, I have to define a snapshot. So the distance, we have, for example, here 2 points, and the distance between them match to the refinement level. So the distance, the tolerance, the distance is the factor times local maximum edge length. We have edge length is blue, and the distance is the factor times this maximum edge length. If your edge refinement defined as 32, for example, as it is in this case, then the snapControl will take 1 point, for example the middle one, and set the next point during the snap process around 32 millimeter radius from this point. Also all points in radius of 32 millimeters. So around. If you have a point in a mesh where fluid flows between two plates, it can happen with the larger tolerance specification, for example, like the next radius. It can happen that this area will be closed because the cells automatically jump to the opposite side of the plate and close the gap. The problem is only where the fluid flows. So for that surfaces where no flows is detected, we don't need to care about this tolerance. So now I can show you if the flow flows here, or let me do the arrow. So it can happen that the cell jump to the next plate and close this gap. So for example, for the walls itself, where we do not have any flow movement, it is not critical, like here or here. That is why I always use the smallest tolerance setting, as it defined here, tolerance 1, in order to prevent such situation where the gap between two plates will be closed. Now we come to the feature snap. I choose for it here the explicit feature snap and define them as true. That means that the snap process will be done by using the HMesh files. That's why I explained the importance of understanding the surfaceFeatureExtractDict. And at the end we come to the mesh quality settings. I use here the default settings, and one point I have to discuss here is the minVol. minVol is the minimum allowable cell volume in the mesh. For that I have a lot of definitions in order to have more control about this part. So why is the minimum volume so important? The simplest reason is that it can be critical for transient simulations due to the current number. A mesh refined in the wrong places can lead to problematic or non-physical results. So in this mesh I set the minVol in two different ways. One way is the minVol taken from experience, like it was done here, know-how. The next way is to define cell volume using the edge length times 3 and divided it to 50, for example. So we have here the minVol of the cell in the mesh, which is maximum 50 times smaller than the min cell volume in the total mesh. In this simulation, exactly the wrong minVol choice leads to the problems with the solution. If we take the minVol as min cell volume divided to 50, the calculation runs well. This definition should be preferred. If we take minVol smaller, as it defined in know-how, from know-how, the calculation will be cancelled, no matter which other settings are used in the mesh control. The minVol definition is essential. So now we have come to an end. I start the meshing process and consider the results. I close the snappyHexMeshDict and run the mesh. So for that I have to execute the following command. So we create 0 folder at first, then when they go to block mesh, then the surface feature extraction, when we do the surface feature extraction decomposition with no 0 file, and after that we run the snappy in parallel, do reconstruct mesh, check mesh. We will search for or write some wrong skew faces and write down some non-ortho faces if they are presented in the mesh. So the decomposition runs. Now Snappy is started. I let it run, and at the end we consider the results. The mesh is ready, and I want to examine the check mesh file. Here you see the check mesh file. It contains in total 3 million cells, close to 3 million cells, and we have here 3 failed mesh checks. So we have some problem in the skewness, some small determinants, and some problem in concave cells. I can show you where the bad cells are located. For this I have to start the mesh case. So for example, I'll open the decomposed case and I want to show the walls blower and walls rotated, maybe zone rotation also. How I can show you this bad skew faces? For that I go to post-processing, constant and skew faces file. I open this case file and let them present as points with diameter 10, dimension 10. Let me do here some cutting plane. I invert it. So here are the places where bad skewed faces, skewed cells are positioned. As you see, bad skew faces are located on different places, so the only one option to improve the mesh quality is to set the parameters of mesh quality controls to those which enable the good mesh quality. If you want more information about it, please contact me. My contact details are written at the end of this video. And now I want to see the whole geometry. For that I enable the internal mesh. So you see the refinement regions, included cylinder here. So, and for me the mesh looks very good. In the next videos I will start the calculation with these settings of snappyHexMeshDict. The minVol will be defined as know-how definition, and the settings for mesh quality should contain these problems in the mesh. So I would like you to see you in the next video, and bye bye.